Hi, everybody. So I wanted to demonstrate really briefly sort of what a join is and how it can help in lots of situations in bioinformatics, but also with protein language models. And so I'm not going to waste a ton of time here. Just want to do a quick video, but briefly, a join in SQL is a case where you might have um, sets of data in a table and need to join them together. So you can imagine kind of a simple case where we have one table, which is a gene ID and a config that it's on. So this we'll see an example, or we'll see in a minute, comes out of a GFF file. And this is sort of hypothetical, but you can imagine we have some other metadata source that has the config and a particular length. Like, so let's say we went through a FASTA file and just made a CSV of contigs to their length. Um, we wanted to join those together, say maybe figure out how long of config a particular gene is on. We can do a join that looks like this. So it's pretty simple. So we have the select statement, which just tells us which columns from which tables we want to display. We're going to select our genes table, and then we're going to join it with our contigs table on where the config ID here is equal to here. So yeah, that's pretty simple, but I think it's important to call that out because I do see a lot of times where folks will use a pattern that looks like this in Python, and it totally works. But it's not going to be as fast, not going to be as simple, not going to be as extensible. And so, if you see this pattern, you might think to yourself whether or not SQL might be an option for you. And so, sort of imagine we have this similar data set where we're going to map with a dictionary the genes to the config ID. So gene one maps to config ID one to also to one. And then we sort of have the mapping of what our table was a second ago. And so this would be our um, single config ID of one, and it has a length of 100, right? And so then you could imagine sort of doing this a la a loop where we're going to do for gene ID and config ID in our genes. We're going to then sort of look up in our contigs length dictionary the length of the config ID, and then we could do something with it, right? So we're in here. We're just going to basically print the gene ID, its associated config ID, and then the length of the gene or the length of the config that gene is on. So again, pretty straightforward. Also, yeah, can run into memory issues, like I mentioned, because these are sort of very large dictionaries for realistic data sets, and it's unlikely that if you had say a metagenomic data set, you'd be able to fit all that in memory. And so this, again, while simple and definitely a good approach for simple use cases, is maybe lacking. Um, what you've seen probably that looks very similar to SQL tables already is a data frame, and so that's something that looks kind of like this. And so we can do basically this join as well. And so we have our genes, our contigs, and we then do the result. Where we're sort of merging the genes with the contigs on the config ID, right? So, excuse me, very straightforward config or very straightforward join, excuse me, and workflow. And this worked really well. I would just sort of mention again that while this can be really good, it sort of runs into questions from some bioinformatic point of view, which is like how do we get this data into these data frames in the first place to even do work with. And then pandas, while good, is sort of notably slower than other alternatives like pandas, or excuse me, like Polaris or SQL actions, excuse me, tend to be a lot faster as well. Um, so we're going to sort of look at an example here in a second of how it can help, how biobear and sort of SQL can help with protein language models. But I did just want to touch briefly on some types of joins for folks who maybe come out of a bioinformatic background and don't know joins. And so this is definitely not comprehensive, and maybe you can use this as a starting point to ask ChatGPT about different joins and their use cases. But all the joins we've seen thus far are inner joins, and so that basically means everything on you have to have both keys have to be present on both sides of the joins, and then only those keys will be sort of like emitted from the join. There's another use case or another option which is like a left join, and that's really useful where you want to retain everything from the left side, so from the genes, and then only join it with contigs on the right side. And you want that data if it appears, but you don't want to throw out genes that don't have a contig. And so you can see here's a mildly contrived example where we have this new gene ID3. It's got a contig of 2. We don't know the length of the contig of 2, but it's still going to be in our output table. So that's sort of like super quick, like how do we join together, how do we join data together, and what it looks like in SQL. I did just want to touch briefly, sort of near the end, about how we can sort of put these ideas together with biobear to support a training of like a protein language model. And so this is from a JGI data set where we have genes, the CDSs from the GFF. We have the contigs, not the CDS nucleotide sequences themselves, but the contigs, and the amino acid sequences in FASTA. And so, what we want to do if we're going to train a protein language model in this case is we're going to maybe take the sort of like translation approach. Of course, you could do like a sort of next token prediction, which is really common. But we're going to maybe sort of say we want to see if we can sort of back translate, if you will, the amino acid sequence to DNA. And we also sort of critical to evaluate how well we can do on those models is we want to get some additional metadata, which is really easy to do in SQL, and use it for group k-fold cross-validation. And so what that is allows us to make sure that an individual contig only appears in either the training set or the test set. Contig sort of maybe a little bit of a stand-in for sort of species or other sort of metadata, or cases where we may not have seen a contig. We get a new data set. We want to like sort of simulate how well our model would do on unseen data. And you can imagine if we're sort of training and testing on sequences which came from the same contig, we might overestimate our performance. And so I'm not going to train the model here. I just want to show how we can use biobear again in SQL to join everything together. And so the first thing we're going to do is load biobear. You can pip install biobear if you want to give it a shot. We're going to create a new session. We're going to create a GFF table from our GFF file, and then we're going to just have a look, right? And so you can see we have the sequence name, the source, the start, the end, the strand that they're called CDS is on the underlying contig, its phase, and the locus tag in question for that annotation. We're also going to load the contigs. So same idea. One small thing is the file extensions for amino acid and nucleotide sequences for FASTA format are often sort of encoded in the extension where sort of FNA is nucleotide. So we're going to load that. We can see we have our ID and our sequence. Basically the same thing for the protein, except we have an FAA as the extension. And then again, we have our genes and our amino acid sequence, or we have our IDs and our amino acid sequences. So now what we want to do is basically join that data together. And it's a little tricky, right? So this is where like it's like, oh, easy joins, and then we're going to throw in some complexity. But the complexity is not so bad. And so what we're going to do, I'm going to start with the from. So we're going to, from our GFF file, we're going to join it on the contigs where the seq name for the GFF annotation is equal to the contig ID. And we're going to join that on the protein table where the GFF, the attributes field, which is a struct, and its locus tag. So we're going to join on where the locus tag. So I'm not going to get into exactly how GFFs are formatted, but this is sort of like a complex data structure, and where that equals the protein ID. Moving back up to the select statement, again, for our k-fold, group k-fold cross-validation, we want our contig. We need to be a little smart here when we're pulling out the sequence. As I mentioned earlier, the strand is called out in the GFF. So if the strand is on the forward strand, we can simply sort of use this substring method to extract that sequence. If it is on the reverse strand, what we're going to actually need to do is extract the sequence and then take the reverse complement of that to get back what the sequence is that would encode that particular amino acid. We get the start, the end, and the strand, and then so some other metadata. And once we've done that, we then have an excellent data frame that we can start using for training, right? So, like if you have an ML engineer on your team and they've never worked in bio, they could probably do something like with this, and like we will see, we can do something again, not doing the training, where we're going to take our group k-fold cross validation. We're going to take our X's here because which are the amino acid sequences. We want to go from amino acid to coding sequence, and so that's going to be our Y. And then we have our contigs where we're going to use as the group. And then finally, we can run our sort of like training loop. And you'll notice here that in our train data set and our test data set, there aren't overlaps. I mean, it's obviously, sort of like not printed fully, but there's not overlaps between our train and our test set. So we would have some confidence that if we did built a good model here on contigs that weren't seen before when we evaluated the model, it's maybe more likely that if we saw contigs, new contigs in a real use case, that our model would be good. So yeah, that's real quick. Just wanted to kind of show how you can use SQL to do some data preparation to get your model or to get your data set into a shape that it is easier to train protein language models or other sort of language models on in this case metagenomics data. All right, thanks.